Welcome to Le Podcast to Philippe. And today we are going deep into a fascinating development in robotics. We are looking at PodWS. You sent over some articles about it.
Yeah.
This quadruped robot. It's really interesting because of how it moves. It moves like a dog.
Yeah.
But unlike a dog and most robots, it's not using electric motors in the traditional way to get around. And that's what we're going to explore today. How does it achieve this? What are the potential applications? Why is this bio-inspired design so interesting? But before we get into that, I just wanted to remind everyone that if you're enjoying these deep dives, we'd love for you to subscribe to our YouTube channel. We are trying to get to 1,000 subscribers. So, if you want to help out. So you sent some really interesting articles about this robot, PodWS. It's not every day that we see something move like a dog, but ditch the conventional motors. So where do we even begin with this?
Yeah, it's a real paradigm shift in how we think about robot locomotion. And I think the core innovation here is this idea of motor-free movement. So instead of having a motor at each joint, which is what most robots do, PodWS uses a system of cables and springs and something called motor synergies.
Motor synergies.
Yeah, that's right. To mimic the natural movements of a dog. And so what this means is it's combining this passive mechanics of the springs and cables with a little bit of active control from the motors. And, it's able to achieve this very fluid, lifelike motion.
So instead of focusing on powering every single joint individually, it's about sort of mimicking the overall way an animal moves.
Right. And they're optimizing this global movement pattern that's inspired by nature, rather than programming each joint very specifically. And that's what makes PodWS so unique.
That's pretty amazing. So how did they even come up with this idea? Did they just start looking at dogs and how they were moving? What was the inspiration behind all this?
It is directly inspired by dogs and canine locomotion. And so the researchers, they did a really in-depth analysis of how dogs move to identify what they call dominant movement synergies.
Dominant movement synergies.
Exactly. And to do this, they use something called PCA, Principal Component Analysis.
Okay.
Which is basically a way of identifying the most important patterns in a data set. So they identified 4 key synergies in canine joint patterns, and these synergies represent these coordinated activations of muscles and tendons.
So it's kind of like understanding the underlying language of how a dog's body moves together.
Right. And once they had that information, they could drastically simplify the control system. So PodWS only uses 4 motors to control all 12 of its joints.
Only 4.
That's right. And so, if you think about how many motors a traditional robot might need, that's a huge reduction in complexity.
That's pretty incredible. So only 4 motors, it's using cables, it's using springs. How did these all work together to actually create the walking and the running that we see?
Yeah, so this is where it gets really interesting from an engineering perspective.
Yeah.
So PodWS recreates the natural elasticity that we see in animal limbs using a few key components. So first of all, they have these Kevlar cables.
Okay.
And they act like tendons, and so they transmit force, and they allow for really flexible movement. And then they also have these carefully tuned springs.
I see.
And those are essential for storing and releasing energy, kind of like what muscles and tendons do in a dog.
Okay.
And then finally, the routing of those tendons throughout the structure is designed to mimic the biomechanical interactions that you would see in a dog's leg. And so it's this combination of cables, springs, and careful routing that allows it to move in this way.
So it's all very carefully thought out.
Absolutely. And what's really cool is that this system allows PodWS to generate spontaneous gaits, like walking and galloping, through simple mechanical interactions. So it doesn't need active electronic control for every single movement, which makes it very different from a lot of robots.
So it's the movement is almost emerging naturally from the way it's built,
rather than being meticulously programmed step by step. I remember reading also that this design allows PodWS to recover from bumps and disturbances really quickly, much faster than other robots. Can you talk about that a little bit?
Yeah, so in testing, PodWS has shown a really impressive ability to quickly regain balance after being disturbed. They did some treadmill tests, and it was able to recover in less than 1 walking cycle.
Wow.
Which is amazing. And this is all thanks to that flexible mechanical design. It can absorb shocks and adapt to uneven surfaces without losing stability.
So it's kind of baked into the design. It doesn't have to think about how to recover. It's just naturally going to do that.
That's right. And this isn't just about surviving a fall. It's really about this fundamental shift towards robots that are inherently more adaptable and less reliant on this constant energy-intensive correction from sensors and complex software.
It's almost like it has a sense of balance just by the way it's built. Right. And this is a great example of what we call embodied intelligence, where instead of all the thinking happening in a central computer, some of the intelligence is built right into the body, into the structure. So the cables and the springs are designed in a way that inherently helps it balance, and this reduces the need for all that complex software.
That's amazing. So embodied intelligence. Really interesting. So we talked a lot about how PodOS is different, and I'd love to compare it to some other robots that people might be familiar with. Robots like Boston Dynamics Spot or Robotics, Animal. How does PodOS compare to those?
Yeah, that's a good question. So PodOS really distinguishes itself through this biomimetic design and its simplified actuation. So if we look at the actuation mechanism, PodOS uses those 4 actuators to control 12 joints through the motor synergies and passive mechanical couplings, whereas robots like Spot, Animal, and some of the Unitree models rely on fully motorized and actively controlled joints, typically 1 motor per joint, so a much more complex system in those other robots.
So PodOS is a lot simpler in a way.
Much simpler, yeah. And I think the inspiration is different too.
Okay.
PodOS is very specifically inspired by canine locomotion, incorporating those tendon-like springs and cables as a core part of its design. The other robots, while they're very capable, they're not explicitly designed to mimic a specific animal's locomotion in the same way. So Spot is more engineered for advanced mobility, Canine for industrial inspection, especially in hazardous environments. And then Unitree robots are often more focused on general research, educational applications, or even personal use because they're a bit more affordable.
Right. Speaking of terrain, how does PodOS handle rough terrain or unexpected bumps compared to these others?
Yeah, so I think this is where the passive robustness of PodOS really comes into play because it's designed with this mechanical passivity and that integrated compliance that we talked about. It's inherently much more resilient to disturbances. Whereas the other robots, while they're very sophisticated, they tend to rely more on active control systems to maintain their balance.
So it's kind of like if it encounters a bump, it can just absorb it naturally.
Right.
Versus the other robots might have to kind of think about it and then engage their motors to compensate.
Right, exactly.
And in terms of tasks, what are some of the things that PodOS might be good at versus these other robots?
So at this stage, PodOS is primarily geared towards biomechanics research, really understanding locomotion in complex terrains, and achieving this natural energy-efficient movement. Whereas Spot, is designed for things like inspection and security, Animal for industrial inspections in hazardous environments. And Unitree robots are often more for general research, education, sometimes even personal use because they're focusing on a lower cost.
Right. Cost is always a factor.
Mm-hmm.
Do we have any insights into how PodOS compares cost-wise to these others?
So the materials we have don't give a specific cost for POS, but the fact that it uses so many fewer motors suggests that it could be significantly more cost-effective to manufacture in the long run. Just to give you an idea, Spot and Animal are in the range of $180,000, whereas Unitree robots are much more affordable. They're around $10,000. But of course, they have different capabilities.
Right. So PodOS might be somewhere in between or even lower because of its simplicity.
Yeah, potentially.
So we've talked about how PodOS moves, how it's different. What are some of the potential real-world applications for a robot like this?
So because it's so good at navigating complex and uneven terrain, it could be really valuable for exploring difficult or dangerous environments. Things like disaster zones, search and rescue operations, or even just logistical support in challenging areas. And because it's so energy efficient and stable, could also have applications for assisting humans in complex urban environments.
It seems like the fact that it's less reliant on sensors and onboard computers just for the basic act of moving could be a real advantage in a lot of unpredictable situations.
Absolutely. It makes it much more robust in certain scenarios because it's not relying on those delicate electronics for just basic locomotion. And, more broadly, I think this bio-inspired approach could really pave the way for a new generation of autonomous robots that are not only energy efficient, but also potentially much easier to control because they're leveraging these natural movement patterns.
So you can see this move away from the traditional motor-driven robots opens up some really interesting possibilities. And the elegance of PodOS is in its simplicity and how it leverages these biological principles.
And what I find really fascinating here is this potential shift in how we think about robot design, moving towards systems that are more mechanically intelligent. And this raises an important question for our listeners. If PodUS can achieve this level of complex movement through this intelligent mechanical design rather than complex electronics, what other areas of technology could benefit from this kind of bio-inspired simplification? Think about the potential for improving energy efficiency, resilience, and even sustainability in all sorts of applications. It's really quite exciting to think about.
It really is.